So the title of the thesis is The Evaluation of the Burning Behavior of Wood Products in the Context of Structural Fire Design. I conducted this thesis at Kent University under the supervision of Professor Bart Mercier, and I was also lucky to be able to do an internship at the University of Queensland for this thesis under the supervision of Professor Jose Torrero. Now, my thesis is about tall timber buildings, and tall timber buildings are being researched by many structural engineering firms throughout the world as a sustainable alternative towards tall buildings, which are commonly designed using concrete or steel. What we see here on the picture is a 9-story building in London made mostly out of cross-laminated timber. Now, what is characteristic for this new generation of tall timber buildings is that they use engineered wood products as a structural frame. Engineered wood products are essentially smaller pieces of wood which are glued together in a certain way in order to create a more structurally efficient product. Now, thanks to these engineered wood products, we can build taller wood buildings than has ever been possible before. However, what I want to talk about today is fire safety, because there is a conflict between fire safety on the one hand and sustainability on the other. Prescriptive building codes throughout the world demand tall buildings to be made out of a non-combustible structure. This means that in our timber buildings we need to cover up most of the timber by plasterboards or other forms of non-combustible cladding, and this partly takes away the environmental benefit. So what I wanted to do in my thesis, or what motivated to do my thesis, is to research the possibilities of using uncovered or unprotected timber for these tall buildings. If we want to use uncovered or unprotected timber elements for tall buildings, we need to go back and establish the physical criteria for the design of tall buildings. In other words, we cannot simply follow the prescriptive building codes, but we need to adopt a performance-based approach. This is what I will talk about in the first point of my presentation. Once we have established the what we need to design for, we can look at the how, so a framework for the fire design of structural timber elements. How do we design these timber elements? I'll quickly compare this performance-based approach versus standard design. So I'll compare performance-based versus how do we commonly design timber elements in buildings. Next, I will talk about a missing link, because there is a key missing link in order to adopt this performance-based approach, which is referred to as self-extinguishment. And this is also the topic on which I did a few experiments in my thesis. Now let's start with the physical criteria for the fire design of tall buildings. This is very important because the fire design for tall buildings is very distinct from low-rise or medium-rise buildings where we are very much used to building with timber. However, because of several characteristics of tall buildings, the height is potentially beyond what fire department ladders can reach, building evacuation might be prolonged, etc. We need to design our structural elements in such a way so that they can withstand a complete burnout. In other words, we should assume that there is no fire brigade intervention. What does this mean for our structural timber elements? Well, this means that we need to design them in such a way so that there is prevention of collapse and fire spread in the building until fire has completely burned out, so until all of the contents of a fire are burned out. Now, once that we have established what we need to design for, we can actually look at how do we design our structural elements. So how do we design these timber elements? And that is why I introduced a framework in my thesis. So this is the performance-based framework, or the framework for the structural calculations of timber. Now, I don't want to go into detail of this framework. If you really want to do that, I would refer to my thesis. I want to spare you of the many beautiful heat transfer equations, etc. I just want to show you this slide to illustrate how, as a structural fire engineer, we do our work. And this does not only apply to timber elements, but it also applies to concrete or steel elements in essence. Now, what we do as a structural fire engineer is we want to calculate the remaining load-bearing capacity of an element after it has been exposed to fire. So what we do is we overdimension our structural element so that even when it has been exposed to fire, it still remains to carry the load. So there is prevention of fire spread or collapse of the building depending on the type of element you look at. So far we have established that the design fire we should adopt, or the fire that we need to expose our structural element to, is a fire that completely burns out. So it is complete burnout. Once we know the fire, we can calculate how much heat from the fire is coming onto our structural element that we are calculating. Once we know the heat coming from the fire, we have to look at the heat transferred through the element. Now, for timber, this is a bit tricky because, as you know, timber is a combustible material. So after it has been heated enough, or if it's in the right conditions, it will start to combust, so it will contribute heat to itself. Once we know all of these things, we can look at a structural model in order to see how much load-bearing capacity the element has. Now, as I said before, the key question here is we need to know the remaining load-bearing capacity of a fire-exposed structural timber element. And the concept of this is actually surprisingly simple because timber is a charring material. A part of the timber will be charred and another part of the timber element will be virgin wood or uncharred wood. And now what is critical here to know is that everything that has been charred away after a fire is essentially non-load bearing, and whatever remains uncharred or virgin wood is load bearing. So what we do as a structural fire engineer is simply overdimension our timber elements so that a part of it can be sacrificed to fire. If it is a relatively short or unsevere fire, this overdimensioning will be relatively small. If we are looking at long fire exposures, for example 2 hours, we will really need to overdimension our structural elements substantially so that even if we lose this part to fire, we still have enough wood left to carry the loads. So it's a pretty simple concept. So you can imagine what is critical here in this story is that we really need to know the thickness of the char layer after a piece of wood has been exposed to fire. No wonder that a lot of research has focused onto establishing simple charring rate models or simple charring rate calculations. It is a common assumption to make that under a fully developed fire stage, so under high and constant heat fluxes, a charring rate is relatively constant. This makes it very easy to calculate the charring thickness because we simply need to multiply a certain constant charring rate times an exposure time. Then the second step is, once the heat fluxes coming from the fire that we see here in this graph start to decay, this means that also the fire is burning out. We simply assume that the charring rate of the wood also goes to zero, so the wood essentially self-extinguishes after it has been exposed to fire. Next, let's just compare this performance-based approach that I just talked about versus standard design, or how we commonly design our structural elements. The standard requirements demand elements to resist a standard temperature time curve. So what we essentially do is we demand our timber elements to resist a standard temperature time curve for a specific amount of time. The specific amount of time depends on the type of legislation. However, if we're looking at tall buildings, the specific amount of time that our wood needs to resist this furnace is a minimum of 2 hours. Depending on the legislation, this can go up to 4, 6, or even more hours. Note that this is very distinct from what we just discussed, where in my thesis I established that in a certain amount of full-scale fire tests where we let the fire completely burn out, the timescales associated to this phenomena was only around 30 minutes. So what does this mean for the structural design of timber elements? This means that if we would apply a real fire condition, let's just call it a real fire condition, we need to overdimension it against 30 minutes of charring. However, if we want to adopt a standard design method, we would need to over-dimension it so it can withstand 6 or maybe 8 hours of standard temperature time curve. This means that we substantially need to over-dimension our structural elements, and this way there is actually a huge potential here to design our structural timber elements a lot more efficient than what we commonly do. However, a very important missing link I haven't talked about is self-extinguishment. So self-extinguishment is quite simply the question, does the charring rate really go down to zero near full compartment burnout? What I've assumed throughout the whole of my presentation so far is that once the heat coming from our external fire, the wood stops to char. However, as you can imagine, there could be cases where a wood element is exposed to a certain fire, for example, to 30 minutes, but after the fire dies out, the wood on itself continues to smolder or burn. So this is a very important question because it will determine the thickness of our char layer. However, why did I make this assumption? This is because there is very little but strong evidence that thermally thick structural elements actually self-extinguishes. And what does this mean? This means that the required sacrificial layer that I've talked about before for standard design might lead to heavily over-dimensioned members. In other words, the standard design methods applied to very tall buildings would lead to almost impractical dimensioning of our wood elements. So there is a huge potential here to design our structural elements again a lot more efficiently. However, quite surprisingly, the question whether or not timber self-extinguishes and more importantly under which conditions this occurs has never really been researched. And the reason of this is that standard design always assumes constant charring over all stages of the fire. However, if we want to adopt a performance-based approach, one of the key hurdles or the key issues that we need to address is whether or not self-extinguishment occurs. And this is actually the key question that I try to answer in my thesis, and that is also why I did some experimental research. So this is a picture of the main experimental setup that I used. It's essentially a vertical setup of the cone calorimeter. On the left we have a cone heater which produces a specific amount of heat flux. On the right we have an engineered wood product sample. I highlighted the glue lines in black of this cross laminated timber. Now what I did is I exposed this block of wood to a specific combination of heat flux and exposure time, and I both varied heat flux and exposure time through a whole series of tests, whilst I was measuring the mass loss rate and the temperatures at different depths inside the sample. Thanks to both of these measurements, I could specifically establish when extinguishment occurs or under which conditions extinguishment occurs. Remarkably, most of these tests turned positive results because within the tested bounds of heat flux and exposure time, most of my elements demonstrated a good self-extinguishing behavior. In other words, once the external heat flux was removed, the self-extinguishment occurred. This was, however, until delamination. So before we can start designing buildings like these in the picture here, there are a lot more issues that need to be addressed, and one of the critical ones is delamination. Now, delamination is an issue that definitely needs further research, and other researchers have indicated that there is a huge potential for problems here, because if you look at full-scale fire tests where delamination occurs, what essentially happens is that we're throwing small pieces of wood onto a fire. So this way we create a huge potential for increased fires or increased fire duration. So this is definitely a topic that needs further addressing. However, keep in mind that maybe through re-engineering of the glues adopted in these products, we could definitely resolve some of those issues. Now we have come to the end of my presentation. I hope via this presentation, I could convince you that the topic of self-extinguishment is a very important topic, and that through research, there is a huge potential here to design structural uncovered timber elements for tall buildings a lot more efficient. However, before we can design these elements efficiently, there are a few more hurdles that need further research. So, thanks for your attention, and if you would have any questions, feel free, of course, to go through my thesis or send me an email. Thanks.